Here now for the second lecture on the Earth's interior structure. If you want to learn more about this, you've got Wikipedia and you've got the textbook. It is section 2.2. And what we're going to do today is we're going to remember that chocolate cake. In last class, I tried to describe the Earth's interior structure based on its composition. Today, we're going to do it based on layers. And so there are 5 different behavior levels, layers, physical layers inside planet Earth. And that might surprise you because there's only 3 compositional layers. So let's see what we need to learn about. And what I'm going to have to do today is introduce geophysics even more through earthquake waves, isostasy, density, and even magnetics, especially as we need to understand the deep interior. All right, so we have these 5 different behavioral levels. The first level is the Earth's lithosphere. And in some ways, these are going to be words you've not heard before. Just like moho might have been new to you last time, xenolith. Today it's going to be lithosphere and asthenosphere. Lithosphere, all right, we got lith. That should show you that this has to do with rock, and indeed it is. This is our solid rock layer of the Earth's surface. This comprises both the crust and the upper mantle. All right, so the mantle actually we're going to split in 2 or 3 compositionally. And so in terms of the sketch that we had last time, we had like a mountain range going down to oceanic crust, and underneath that mountain range we had a keel of continental crust, and here's our oceanic, yeah? What was this called? The contact between the crust and this was called the mantle. Now, the asthenosphere, lithosphere contact we also can draw in, and it would be something like this. And so this area of the upper mantle plus the crust is the lithosphere. So the lithosphere goes from the top of that mountain down to the bottom of this structural unit. The lithosphere is also this, from the bottom of that to this. And the layer underneath, and we're going to get to it in a second, is called the asthenosphere, and it behaves structurally different than the lithosphere. So the lithosphere is crust plus supple mantle. I've said it a number of times. Students struggle with this. Underneath oceans, it's about 100 kilometers thick. Underneath mountain ranges, it can be up to 300 kilometers thick. And in a lot of ways, this has to, the lithosphere is floating. It is isostasy. So I'm going to actually put this in, isostasy. I taught this with the concept of glaciers. I'm going to try it here with a picture. We'll actually do a couple pictures here. So this is how the lithosphere works. A glacier, sorry, here we go. All right, so we have the mantle, 3.4. This is gonna be our asthenosphere. And this area over here is our lithosphere. And it is floating along. In this picture, it's actually supposed to be like wooden blocks floating in water. And of course, here we have ice floating on water. And this idea of floating, of gravitational equilibrium, is isostasy. So I would like you to know that the lithosphere is floating on the asthenosphere, and the topography that we see is produced by this topographic equilibrium. All right, much more on that in future in your geology career. The other aspect of the lithosphere I want you to know is that since it is the solid, brittle part of our Earth structure, it actually does break into plates. And so when we talk about plate tectonics soon, the fragments, like here's the African plate, this structural unit that is pulling away from the South American plate, these are actually go all the way down through the lithosphere. It's not just the crust that's pulling apart. The lithosphere is pulling apart. So then the Indian plate is slamming into the Eurasian plate, making the Himalaya mountains. And this is the full lithosphere that is doing that collision. So in terms of lithosphere, the last note I would want you to put down as like a buzzword or something is it will break into plates. And it's these plates that are our plate tectonics. All right. The next layer down inside the interior of the Earth is the weak mantle, and it is called the asthenosphere. Asthenosphere. In Greek, I believe astheno means weak, And so when you picture what is the asthenosphere, it is mechanically weak. Other words like plastic or viscous are appropriate. Plates are slamming into one another. I just said they were rigid. Well, it's actually this asthenosphere that is flowing that is actually causing those plates to drive and crash into one another. So if we had a cross section through the Earth, and here is our core, and here is our mantle, well, we should put a dotted line. And this can be our lithospheric mantle, this could be our asthenospheric mantle, and then we're actually gonna have our lower mantle. And that is so poorly drawn to scale, I can't even believe it. The part I wanted to put in here is that I wanted to put in some arrows showing flow, that mantle will flow down and mantle will flow up. And the flowing mantle is the asthenospheric mantle. The heat and the pressure do make minerals weak. I'm going to put that minerals are weaker, but there's also probably like 0.1% melt. And it's that little bit of melt that also helps make the asthenosphere be able to flow and move and drive plate tectonics. Now the asthenosphere is about, it's 400 kilometers thick. At 660 kilometers depth, there's a discontinuity. I taught you about a discontinuity last time, a compositional discontinuity called the MOHO. At the 660 discontinuity, which is just called the 660 discontinuity, it is a density change. And we know there's a density change here because earthquake waves change in their speed. So let me show you a graph of how earthquake waves change through the interior of the Earth. And so here is velocity. And so we have S waves and P waves. You might have not learned about that yet, but each of these are earthquake waves. And what we see, okay, so here we are. We're going down through the Earth, and at 660, notice there's a density change. There's a step function. At 660 right here in the P waves and in the S waves, there is a jump in the velocity and in the density of the material. And we consider that 660 discontinuity the bottom of the asthenosphere and the top of what's called the mesosphere. And the mesosphere we just also call the lower mantle. And we don't know much about the lower mantle. It's very hard to sample the lower mantle. It doesn't look like much happens down there. In fact, we could even say something like no little. And relative to the asthenosphere and the lithosphere and even the core, we know less about the mesosphere. But one thing I do want to point out to you about the mesosphere, I'm going to do it in red here. Here's the mesosphere in terms of its density. And here is it in terms of its earthquake wave speed. Notice how smooth that line is. There's not a bunch of jumbles and breaks like there are up here in the shallow mantle. And so what we think is that this is a fairly homogeneous, stiff, maybe it moves a little bit, portion of the interior of the Earth. If there was a lot of heterogeneity, we would expect to see the heterogeneity show up in terms of density jumps, but we don't see that. Instead, we see this nice smooth increase. So maybe the mesosphere is actually fairly boring. All right, now what about the core? Before we get to the core, I do need to put in one more thing about earthquake waves. Actually, let's just go ahead and do it. I told you about P and what S waves. Let's do this in our notes. Earthquake waves. There's a variety of different types of waves that are produced by earthquakes. Two of them we're going to name right now. We're going to name the P wave and the S wave. And they move with a different direction. S waves have more of a sinusoidal kind of behavior as it moves through a material. But a P wave, and that's how you picture a wave, like an ocean wave. A P wave is different. A P wave is a compressional wave. So if we have a material, when a P wave is in that material, it's compressed together. And then, so this area right here and this area right here are evidences of a P wave compressing a material and then expanding. Another thing I would like you to know about earthquake waves is that the speed of the wave correlates with the density of the rock. And so by measuring earthquake speed, we can also then make up estimates for the density of the interior. And now the last kind of geophysics concept to put in before we get to the core is the idea of a magnetic field. You use magnetic fields in your day-to-day life. For example, a magnet on a refrigerator, that would have a strength of about 100 Gauss. Well, the Earth has a magnetic field of about 0.5 Gauss, so it's much weaker. This is Earth's. This would be a refrigerator magnet. I don't want to write all that. Magnet, fridge. With Earth's magnetic field, I would like you to picture something like, here's planet Earth, we have our North Pole, we have our South Pole, and there are actual magnetic lines going through our planet. And it's this magnetic field, and you can look up much better pictures on the internet, it protects us from a lot of things. It protects us from UV radiation. It protects us from what we say, solar particles. If we did not have our magnetic field, we would be like Mars, stripped of atmosphere and just burning under UV radiation. So it's really good for us. And by the fact that we have a magnetic field definitely tells us something about the Earth's interior. All right, and it's going to tell us about the core. So number 4 in our layers of our structure, we're going to have the outer core. And the outer core is different than the inner core. The outer core is iron plus nickel compositionally, and it is totally liquid. So we're going to say iron plus nickel as liquid. It's 2,400 kilometers across. It's a huge body of moving fluid liquid, and we know that the liquid is moving because of our magnetic field. By magnetic field. The other thing that we know about, well, I guess that we know that it is liquid, and number 5, inner core, it's solid. Inner core is solid, and it is solid iron plus nickel. And we know this because of P waves and S waves. So I'm going to put in this picture, see if I make it big enough to where we can actually read it. That's let me move it down here. All right. So here's the key about S waves. S waves cannot go through a liquid. And so when we look at earthquake waves, if an earthquake were to occur right here, earthquake waves travel through the Earth's interior, but they get blocked by something, and there's something called the S-wave shadow zone on the far side of the Earth where the earthquake waves are blocked by the liquid outer core. P waves can travel through a liquid, and so notice how they are going right on through. So by seeing P waves but not S waves, we know that the outer core is liquid. So we're going to say P waves travel through, S waves blocked. And this is like, I would say, like the biggest and best reason for us knowing that the outer core is liquid. Now let's talk about this inner core. The inner core, we cannot get any information from our S-wave paths, but we can get one thing from the P-wave path, and this was found out by Dr. Inge Langman in 1936, and what she recognized is that there is actually a P-wave shadow zone. There's a huge S-wave shadow zone, but there's also this weird area where P waves should show up, but they don't. And that's because waves are getting bent and diffracted as they pass through. Oh, what am I trying to show here? I guess it's actually this right here. Anyways, the earthquake waves passing through the inner core are diffracted a little bit, and they're not exactly where you think they should be. So let's say this. We know the inner core is solid by P wave slight misplacement. Right? It's not the P wave shadow zone. That's wrong. It's actually just this slight misplacement here. We've learned since 1936 that the inner core was solid. And the other way that we could know this is through what's called a phase diagram or phase stability. And so let me show you what I mean by this. Here is a PT diagram. And we can say, where does liquid iron and solid iron exist in temperature and pressure space? And at, let's see, the Earth's interior is around 330 GPa. It's incredibly high pressure. The temperature of the Earth's inner core is around 5,700 Kelvin, which is almost the temperature of the sun. So it's about right here is where we would place the Earth's inner core. And what's really cool is the phase stability between solid iron and liquid iron plots around this line here. And so where do we plot? We plot in the solid field, and therefore the Earth's interior, the inner core, should be solid.